Warm welcome, everybody. Thank you for joining. Wow, in this one, we're going to be interpreting the meaning of closest with math. Of course, math is going to analyze the shit out of everything, basically. And distance is no exception. We overanalyze what it means to be close, what distance is. And in this one, we have to find the closest point on this graph. It has to be a point on x squared that is closest to this given point. So it'll help if you have a diagram or a graph, a sketch of the graph, to kind of see what that looks like. You should know how to do that very quickly. It should not take you much time at all. If you're like, I don't know how to graph this, I don't know how much I have to graph. Well, you know what x squared looks like, so that shouldn't even be a question. But look at this point. So just make sure that that point is like reasonably in frame, and you'll be okay. So here we have 0, 0. Let's say that's 1, 1, 2, 4. So it's going kind of like that, and it's doing the same thing this way. The point that we have, 2, 1/2, that's like right here. So just for a visual, we should expect our closest point to be like somewhere kind of near there. Excuse me, maybe a little bit past 1. I don't know for sure, but it seems like it would be a little bit past 1. Here's 1. So maybe around x equals 1.1 or 1.15 or something. All right, so how exactly are we going to approach this? How is this an optimization problem? Well, closest does mean we are optimizing something. Remember that optimizing just means finding a maximum or minimum situation. What are we doing? We're minimizing distance. Yeah. So we're minimizing the distance between some point on the function. We don't really know what its coordinates are. But if we had to put them in general terms, the coordinates of this point are x, comma, what would be the y value if I were to plug in x to the function? I would get the function x squared. So we want to find the minimum distance between some x and x squared. We don't have any specific value on that yet. And 2, 1/2. So let's write up the distance formula. And then there's a little bit of a nuance here that I want to mention. So we have x squared minus 1/2, that is squared, plus x minus 2 squared. Now the interesting thing about minimizing this, you'll notice there's not really a specific constraint, because x can be any value on the parabola, but obviously it's not very close if it's like over here, or even if it starts going up here. Even here it's a little bit too far. Clearly we're going to get an answer that's somewhere in this ballpark, kind of close to x equals 1. So there's no domain restriction, but there's something really useful. Because we don't really want to take a maximum of this, you have to take a derivative, and it's kind of gnarly. You could open it up if you want and stuff, but it's a little bit gnarly to take a derivative of and then try to work with. What I want you to observe, and you're going to have to use this in problems like this, you can simply state that d is a minimum when the inside of the root is a minimum. So finding the x value, which minimizes this function of d, is the same x value and serves the same purpose, therefore, as minimizing the inside. So if I can find a minimum of this function, x squared minus 1/2 squared plus x minus 2 squared, then we're good to go. And this is where algebra skills come in handy big time. You should be able to FOIL this very quickly. See how fast I did that? It should be that fast. X squared minus 4x plus 4. You can put things together. Of course, the x squareds are going to cancel. The 1/4 and the 4 makes 17/4. So we have x to the 4th minus 4x plus 17/4. Our goal is to minimize that. So now we're ready to take a derivative. All right, there's no stopping. This train is rolling. Minus 4. Very simple to do. Now you're going to have to recall something about a sum or difference of cubes when you're factoring. You want to set this equal to 0 or undefined, but it's never undefined. It's always defined. So let's just factor this. And yeah, this is what we know as a difference of cubes. We're going to end up with the SOAP model, same sign, opposite sign, always positive. And if you don't remember the sequence here, it goes A, so that's just x. Then it's opposite, and it's each of these, 1 times x, so that's just x. Always positive plus this squared is just positive 1. So there we go. And I also want to remind you, so many reminders of pre-calculus here. So you got to know your pre-calculus to be successful in calculus. You just can't get around that. Remember that this quadratic expression is irreducible into real numbers, has no real solutions. So like, don't waste your time trying to find how to factor that down or break that down. You're not going to find any values to do that. If you want to see it for yourself, you can use the discriminant, b squared minus 4ac. That's the part that would go inside of the square root, and that would be 1 minus 4, which is negative 3. And so that can't be in the square root, so there's no solutions that are real which come from that. But we do get a nice solution here. X equals 1 seems to be of interest. There's a critical point there. And again, it is easy enough to just take the second derivative. F double prime is simply 12x squared, which is always greater than 0 if x is greater than 0. It's always, like, it's never negative, I should say. So when x equals 1, in fact, I think I'll just write this. F double prime of 1 is 12, which is greater than 0. So f of x is concave up at the flat point, x equals 1. So it has a minimum. Now that's not a point, that's just an x value. So we need to find the point on the graph of x squared. Remember that f of x equals x squared. That's where the dot has to be on. So it turns out it was right at x equals 1. F of 1 equals 1 squared, which is 1. So 1 comma 1, that is the closest point on the graph. Who would have thought? I guess my drawing wasn't terrible. So what did we learn here? We learned here that there's this kind of special trick when it comes to the closest to a point. We use the distance formula, but you don't have to take a derivative with the square root on it. You can take the hood off and, kind of breeze through this more polynomial type maximum or minimum problem, as opposed to having to worry about like 1/2 powers and stuff like that. You should still work on those. Be good to work with radicals. You need to be good with them, but if you don't have to do it like on a test and you can find an easier way, absolutely exploit that. And then we use the second derivative test here. Of course, if you want to use the chart with f prime, you can. See what that chart would look like. We'd have 4, which is always positive. You don't even really need to list positive constants. We have x minus 1, which is obviously 0 when x equals 1. And then we have this x, I forgot to put x squared. Sorry. X squared plus x plus 1. That should be always positive because it never has any zeros, so it must stay positive. Just like you in life, you must stay positive. And we have a sign flip 4 is always just 4. And so overall, the derivative f prime hits 0 at 1, and it goes from negative to positive, which tells us that this is a relative minimum. Okay. So I think that was pretty straightforward. Just aside from that little trick, once you get around the fact that we need the distance formula, there's not a specific constraint, but we can sort of hack by taking this square root top off. From there on, it's smooth sailing. Regular analysis of maximums and minimums. So even though we got really nerdy and described closest in terms of the distance formula, it makes perfect sense to do so, right? Because the distance formula tells us the distance between 2 points, even if one of those points is not a specific point. It's a point on a graph, so its coordinates are simply x comma f of x. Whatever the function is, that's what it's going to do to the x, so that's what the y value is going to be. All right, so that's enough blab out of me. See you guys next time.